Hey there! Welcome to today's video on using the properties of combinations of continuous functions to determine the intervals over which the given function is continuous. So here I have three different examples to give you a little bit more insight into the process. Now in part A, I have the function f of x is equal to 4x cubed times the square root of x plus 15. Now this function f of x is made up of two functions multiplied together. So I have the function g of x, which is my 4x cubed, and h of x, which is the square root of x plus 15. Now these two functions are multiplied together, as I said, so we want to look at the interval for which each of these are individually continuous, and then the product of those two will be continuous over those values of x that meet both conditions. So here for g of x, it's equal to 4x cubed, which is a polynomial, and this polynomials in general, are continuous over all reals. So that's the interval negative infinity to infinity. Now h of x is equal to the square root of x plus 15. Remember, if there's no little number in the crux, the index is assumed to be a 2 for square root. If there is a number in there, if it's an odd number in there, it would be continuous over all reals. But if it's an even number as an index, then it has to be that you have your even indexed root of a non-negative number. So whatever they're taking the square root of in this case has to be greater than or equal to 0. So for h of x, this x plus 15 has to be greater than or equal to 0. And then subtracting 15 from both sides, I get x is greater than or equal to negative 15. The interval notation for that includes the negative 15, so we're going to have the bracket, and the x's that are greater than or equal to that are to the right of it, so off to infinity. Now the function f of x is continuous on the interval that meets both of those conditions. So it has to be the strictest of those, and that would be the interval negative 15 off to infinity. And remember, we always use a parenthesis at the infinities for the numerical values. If it's or equal to include the endpoint, we use a bracket. If it doesn't have that or equal to, we use a parenthesis. Let's go on to part B. So for part B, the function f of x is made up of a quotient of two functions. It's the quotient of g of x is equal to x squared minus 16, and h of x, which is equal to x plus 4. Now remember, for quotients, you have to make sure that you remember that the function is continuous for the restrictions of the two. Also, you have to make sure that the denominator is not equal to 0. So while g of x equal to a polynomial, x squared minus 16 is a polynomial, is continuous through all real numbers, so negative infinity to infinity, h of x equal x plus 4 on its own is also continuous from negative infinity to infinity. But because that is in the denominator, for my function f of x is continuous for, well, both of those are negative infinity to infinity, but I can't allow the denominator to be 0. So x plus 4 can't be 0. That means x can't be negative 4. So when I write that, f of x is continuous on the interval negative infinity leading up to but not including negative 4, and we do that with a parenthesis, union, pick up on the other side, so parenthesis negative 4, and then off to infinity. Okay, part C. So for part C, I have a little bit of each of those cases. I have a square root of x minus 8, but that's also sitting in the denominator, so I also need to make sure my denominator is not 0. This function is made up of two different functions. G of x is equal to 9 sine x, and h of x is equal to the square root of x minus 8. Sine x is continuous throughout all real numbers, and multiplying that by 9 doesn't affect that situation of being continuous. So I have negative infinity to infinity for the interval that g of x is continuous. H of x has that same sort of situation that part A had with the h of x. It's a square root, so what's under the square root has to stay greater than or equal to 0. My x minus 8 has to be greater than or equal to 0, so my x has to be greater than or equal to 8 for h of x. Now the x's that are greater are to the right of it, so we have our bracket at 8 off to infinity for our continuity for h of x. Now for f of x is continuous. Not only on the strictest of these cases, but also I can't let the denominator be equal to 0. So I need to make sure that that x minus 8 is not 0, so x cannot be 8. That means when I look at this interval bracket 8 off to infinity that I had for the strictest of the cases, but it is also the one in the denominator, I cannot include 8 either. So instead of a squared bracket for the interval for f of x being continuous, it's going to be a parenthesis at 8 and then off to infinity. So there you have 3 more examples of how you use the properties of combinations of continuous functions to determine the intervals over which the given function is continuous. Hope this helped, and I'll see you in a future video.